Welcome to my project bazaar. We are going to see the product for improving nested loop pipelining on coarse-grained reconfigurable architectures. Next, we are going to see the abstract for our product. Coarse-grained reconfigurable architectures have the potential to offer performance approaching an ASIC with the flexibility within an application domain. Configurable computing is a subset of spatial computing that provides computation and communication resources that can be configured or programmed at load time or runtime. FPGAs are a common example of a load time configurable computing system, while CGRAs such as RAPID and PIPRange are examples of runtime configurable computing systems. Usually, a reconfigurable block is combined with a general-purpose microprocessor. In this way, the processor maps the instructions that can be done efficiently to reconfigurable block, and the microprocessor performs instructions that cannot be done efficiently in reconfigurable block. The FPGA uses fine-grained reconfigurable arrays of functional elements, but this creates burdens which is less efficient due to huge routing area and poor routability. Coarse-grained architectures provide better programmability and performance. In particular, coarse-grained reconfigurable architectures have been proven to be effective solutions for computation-intensive applications such as multimedia applications by providing higher efficiency in terms of power, area, and configuration cost when compared to fine-grained architectures such as FPGAs. However, as is the case with many other forms of reconfigurable computing, the practical drawbacks of CGRA have mostly been on the software side, primarily due to the complexities involving mapping applications to utilize such architecture. The application mapping is usually done manually, which is an extremely difficult task since a comprehensive understanding of the target architecture is required of the application. Processing elements or logical units that can perform basic ALU operations or load store operations, which can be dynamically configured through the configuration cache. It may consist of homogeneous or heterogeneous logical blocks. PEs are connected to each other PEs through the interconnection network. They enable sharing of resources among them. In our project, we create an ALU architecture which can perform various operations. The input is 32 bits. The ALU unit can improve the performance of an processing element. A single ALU is created which can improve the computation. Next, we are going to see the flow diagram for our product. The ALU architecture mainly used to perform the arithmetic and logical process, and the arithmetic process consists the adder and subtractor and multiplier architecture. The max input section to change the output based on selection process. The selection process used to modify the output unit architecture. The ALU block to optimize the internal architecture. The internal architecture to consume the 3 arithmetic operation and 5 logical operation. The buffer architecture used to store the output with delay time for the ALU operation and to check the required selection signal. The max operation used to find the output and to store the max input and to select the input selection signal and to display the output result. One standard method of specifying an architecture is using a hardware description language such as VHDL. However, we have found that one invaluable debugging technique for CGRAs is to visualize how an application is mapped to a given architecture, represented by a data path graph in both space and time. Therefore, we have put considerable effort into making visualizable data path graphs. The ALU architecture mainly used to perform the arithmetic and logical process, and the arithmetic process consists the adder and subtractor and multiplier and shifter architecture. The logical process consists of the AND gate and OR gate architecture. This architecture is to design the structural methodology. The operands A and B enter the logic unit through registers controlled by the gated clock, like the arithmetic unit, giving it exclusivity of operation only when required by the ALU. The ALU block is to optimize the internal architecture. The internal architecture is to consume the 6 arithmetic operation and 2 logical operation. The arithmetic operation requires more time and high path delay and reduces speed. So the modification process is mainly focused by the carry propagation process. The input bits are to be applying the ALU circuit. The 8x1 mux architecture is used to select the operation output data bits based on arithmetic and logical operation. The mux architecture consists the overall internal ALU architecture, output data bits, and to optimize the selection processing time using look ahead clock gating technique. The mux input selection is to change the output based on selection process. The selection process is used to modify the output unit. Finally, we are going to see the output for our product. To create a new project, click on File and then on New Project and specify the folder to which you have to save your project. For the source file, click on the project and create a new source. If you want to add an existing source, then click on Add Source. To see our result, we can simulate. Click on the simulation and then main, and then double click on the simulate behavioral model. The output will be shown on the iSIM. The iSIM has the output for our product. There are 2 inputs, one output, one selection line. A is the first input, give a binary value of 32 bits. Click on enter, and then for B, give 32 bits input. And then for the selection line, here I mentioned 0 and 0 and click on run. The output will be 64 bits. Minimize the iSIM. For the implementation result, click on implementation and then on the implement design. Here I run the process. The ALU architecture we have implemented has a better computation than the other architectures. The ALU architecture has multiplier, subtractor, AND gate, OR gate, NAND gate. The coarse grain architecture has a nested loop pipelining, and the processing element has the ALU. The processing element has a number of functions in which the multiplexers are used to select the input for the ALU. The output from the ALU is stored in the registers. We can implement the design and can view the synthesis report and the generation process. The time delay of the program can be viewed. Coarse-grained rectifier architectures is a promising parallel computing architecture combining the performance of application-specific integrated circuit with the flexibility of general-purpose processor, which is typically composed of a host controller, a processing element array. The processing element has the ALU unit. The time generation process shows the runtime of our program. Here the implementation design has successfully executed. Then for the synthesis report, click on the synthesis report and advanced HTL synthesis report. Here we can view the number of LUTs, number of flip-flops used for our project. Here number of slice registers is 3, number of LUTs is 6, number of logics is 6, flip-flops used are 6. For the timing report, click on the timing report. Here we can view the delay time of the program. The delay time is 1.005 nanoseconds. For the synthesis report, click on the synthesis stick and view RTL schematic. Then click on add and create schematic. The schematic will be created. The logical diagram will also be created. Thank you.